Welcome to Learn Extra Live Grade 10 Physical Science. Finally, your day has come for your favorite lesson. I'm Katleho and this is Atik. Hello, Atik.
Hi, Katleko. How are you doing?
I'm great, thank you. Guys, Atik is one of our top 10 presenters. He will be joining us for the entire show today. He's really excited, aren't you?
I'm ecstatically excited.
Exactly. So you guys need to get chatting. Please tell them where they can find us.
www.facebook.com/learnextra.
Awesome. So you guys know the drill. Jump onto the page, get chatting to us, ask questions, ask anything that you need, because that is what we're here for. Today you have both of us, so make sure that you have as much fun as we have. Of course, you're seeing right. We have our Simba, can you see those? Yes, Simba Cheetos. It's really awesome. I've been dying all week, like even last week, just to have like one packet of these. But these are for the random act of kindness, guys. You guys are, you just urged or asked nicely to post some pictures on our Facebook events wall of anything that you have, any random act of kindness that you can do for anyone in your community and beyond, guys. It doesn't take much of your time. It's just a smile. Or what can you think of, Atik?
Maybe helping a little brother or sister do homework.
Exactly. Plus you're a mindsetter, so you know more than they do. So jump on to the page, send us your random acts of kindness, and you can stand a chance to win this entire hamper. Now this hamper has chips, it has a mindset lanyard, it has a mindset pen, it has a Cheetos notebook, it has 5 CDs, guys, not just 5. It has Unati, it has Malik, it has Kaya, it has Donald, and it has some love song because it is the month of love and we are spreading love. So make sure that you are the one that wins this package, guys, because it's really awesome. Today we're doing physical science with Tracy. Tracy, how are you?
I'm doing well, thanks, Katlego.
Awesome. Please tell us what we'll be doing today.
Brilliant. Well, mine said is it's really important that you pay full attention today. We're going to be looking at electron configurations and the periodic table. And electron configurations are something that is fundamental in terms of your understanding. Grade 11s and grade 12s often still struggle with this. So I really highly recommend that you take out that exam pad, that you've got your pen and notepad ready, that you've maybe downloaded the notes already, and that you're going to be working really well with me today. Katlego, anything else?
And nothing else. You can actually just take it away. I'm sure they're dying to know what's happening today.
Absolutely. Well, thank you so much. We are really looking forward to this. And as I said to you, chemistry, in terms of all the bonding that you're going to ever do, chemical reactions, it's so vital that you make sure that you have a very good understanding of electron configuration. So let's get into it. Electron configuration and the periodic table. This is a simple periodic table that we've got in front of us. What we're going to be learning today, we'll be focusing on drawing electron configurations. So by electron configurations, I'm looking at how electrons are structured around atoms and various models or pictures that help us to understand those. Show that elements are arranged in increasing atomic number on the periodic table. Link the arrangement of the periodic table with atomic structure. Link periodicity, which means the repeating patterns of the table to the various chemical properties of the elements, and learn about trends. So let's get stuck into electron arrangement. Electrons are found in energy levels, and when we say energy levels, we're thinking those ones that are closest to the nucleus will have the least amount of energy, and as the electrons are found in energy levels further away from that central nucleus, they will have to have higher energy. They would be moving in regions of space that are called orbitals. Now let's just take this little bit away so that you can note this very important word, orbitals. Orbitals are regions of space where an electron could be found. There's a higher probability of an electron being found there. They are not spherical rings or different shapes, but they are clouds, electron clouds where electrons could be found. There are various ways that we can represent electron configurations, and we're going to discuss 3 of those today. we're going to look at a concentric circle model, a Lewis diagram, and an Aufbau diagram. And this is also called an energy level diagram. You could very easily in an exam question be asked to draw these models. And so not only are they important for your understanding of bonding and everything else that's going to come in chemistry, they are important in terms of answering exam questions. You will be asked to draw these. So let's start with the simplest, the concentric circle model. For the concentric circle model, we are considering energy levels with the electrons found on those energy levels or in those energy levels as circles, concentric circles. And in the first ring, 2 electrons can be found. In the second ring, 8 electrons can be found. And in the next ring, third ring, 8 electrons can be found. And we're not going to go much further than that. So let's have a look at how this would be done. I've got an example here of neon. Neon has 10 and a number 20. What do those numbers mean? We spoke about this last week. The 10 represents the atomic number, okay, which means the number of protons, positive, okay. The 20 represents the atomic mass, and I'm going to change color to indicate that it would be atomic mass. And for atomic mass, you are thinking that is the protons and the neutrons. As we have a look at that, if it's got 10 protons, for this atom to be neutral, if it's got 10 protons, how many electrons must it have? Well, for it to be perfectly neutral, it should have 10 electrons as well, so that overall the charge is 0. There is no charge. So let's go with this atomic model and fill in the electrons. We're going to fill them in as little circles. I said 2 in the first, so 1, 2 in the first. Now we go 8 in the next, so 1, 2, 3, 4, 5, 6, 7, 8. Check with me quickly. Is that a total of 10? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 electrons shown in those energy levels. Now, the reason I've shown this one to you specifically is because I want to indicate to you how to arrange them. The electrons I want to recommend is that you put those electrons on the compass points as you work your way around. It's going to be very helpful to you because it's going to show how many spaces there are available for bonding. And we often use something called the octet rule, which is saying if you've got filled outer energy level full of, in this case it would be 8, and apart from helium, which has only got 2, so it's only the 2 in the central ring would be filled. If it's got this filled outer energy level of 8, almost like 8 people sitting around a table, there is no more space for any electrons. So there's no need for that atom to bond. And neon actually is one of those noble gases. It doesn't bond with anything else because it's got a stable electron structure, a filled outer energy level. So we've got 2 key words that I want you to note: valence electrons and core electrons. What do you think the core electrons would be meaning? The core electrons must mean the inside ones, right? So the core electrons in this case would be neon's 2 core electrons. They would be ones that are found in the inner energy levels. Whereas the valence electrons, that was the core, the valence electrons are those that are found in the outermost energy level. We're going to use those 2 words a lot as we discuss electron structure. Let's move on to the next, a few of these in terms of practice. Now I've included here Lewis diagrams. Now, Lewis diagrams are even simpler than the concentric circle model because they only consider the outer ring, the valence shell, which is helpful. So only valence electrons are shown as either dots or crosses around the symbol for the element. Let's consider carbon. Now, you're going to need to know how many protons carbon has so that you can work out how many electrons carbon has. So I've got a periodic table. Let's reference it quickly. Find carbon. Carbon is over here, number 6. That 6 is the atomic number or the number of protons. So we can go back and write carbon and note it has 6. So let's try out this practice the original one, where we did the concentric circle model. So I've got 2 rings that I'm drawing, and we're going to go 1, 2 in the first, and now I'm suggesting you work with compass points as you go around. 1, 2, 3, 4, 5, 6. So it's got 2 core electrons and 4 valence electrons. Now for this Lewis diagram, we only need to draw the outer ring, the valence electrons, because those are the ones that are going to be involved in bonding, involved in interacting with other elements. So for a Lewis diagram, we're going to just draw, and I'm going to use little crosses to indicate those 4 valence electrons. Let's go on and try another one. We're going to work with oxygen. So I'll change pen color and let's work with yellow for oxygen. Oh, that was, I think, a little bit too far. Let's find oxygen again. Oxygen, let's draw its valence electron, the ring structure, and I need to go to a periodic table, find oxygen. We've got oxygen over here, oxygen number 8. So atomic number, and I'm going to write up here 8 protons, 8 electrons, because overall it's an oxygen atom, so it must be neutral, no overall charge. Let's go. If we've got to make 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. Now, as I suggested to you, you want to work around on the compass points because it's going to help you to identify where there are spaces for the substance to bond. How many electrons would it gain or lose in order to make sure that it gets to a filled outer energy level? So let's have a look for oxygen here. And we've got oxygen. It's got a lone pair and another lone pair. These guys is what I'm going to call a lone pair. They have paired up already. But notice there is space, 2 separate spaces where oxygen can take up extra electrons. And so usually when oxygen bonds, it's going to form an O2 minus ion. We'll come to that in a few weeks as we look at bonding. Let's keep going. The last type of model I need to look at is sometimes called an Aufbau diagram or an energy level diagram. Now these tend to be the most complicated, so let's spend some time working on those. Aufbau diagrams have these little box structures where we have not just energy levels, but the shells in which, or the orbitals in which those electrons would fit into. So you have a 1s, a 2s, 2p, 3s, 3p, 4s, and it can continue. This first band is the first energy level. The next band is the second energy level. The third band, the third energy level. But in terms of filling up, we're going to always start from the bottom and fill up with electrons. Now, the electrons are shown as little arrows going up and going down. The reason going up and going down is because those electrons, in order to not have a significant repulsion, they are always aligned with opposite spin. So the one spins one way, the other spins the other way. Okay? Now, there are a couple of rules that we need to follow as we work through Aufbau diagrams. Each orbital or little block can only hold 2 electrons, called an electron pair. An electron will always try to enter one with the lowest possible energy level. So you're going to start from the bottom and work your way up. An electron will occupy an orbital on its own, because remember, these are electrons, and so they're going to, if they have the same charge, repel each other. So they will start with their own space, and then, if necessary, they will pair up. So an electron would rather occupy a lower energy level with another electron before occupying a higher one. If it has to, it will pair up. In other words, with one energy level, electrons will fill an s orbital before starting to fill higher up p orbitals. And the s subshell can hold 2 electrons, while the p subshell can hold a maximum of 6. And what we're going to do is, when we come back from this break, we're going to look at drawing some of these, and we've got lots to practice on. So make sure you come back after the break.
Thank you, Tracy. As you said, guys, stay on those seats. There's so much to learn. There's so much to do. And we'll see you right after the short break. Okay, so after the break, I like saying welcome back, Mindsetters. If you have just joined us, I hope you haven't, because it has been such a great and informative show. I hope you guys haven't missed a single word. Atik is here with us. So you've been here for almost half the show now. How does it feel?
It feels great.
It does,
It does. It's very exciting learning new things. I was never a good student with physics, and I'm getting to learn some of the things I missed at school.
That's awesome, hey? And I hope you Mindsetters are also learning so much. Remember, guys, I hope you guys remember, and you've already started doing this, but those of you who don't, there's such an awesome site that we have. That site is learnextra.co.za/live. I'll put it up on the page for you guys to see. This is the site that you guys can download notes, you can download the schedules or see what we'll be doing in the lesson. You can download the videos of what we've been doing today and other days and last week and the week before. You guys must just go onto that page and check it out. It's really, really awesome. Start downloading your notes now so that you're following along with everything that Tracy's doing, just so that you get so much more absorbed in. Over to you, Tracy.
Thanks so much, Katlego. We're going to start with some questions on Aufbau diagrams. Remember, they could be asked as energy level diagrams, because as you have a look at it, and I've started with the blocks there, these bands are showing the various different energy levels that a substance would have. So we've got a start with nitrogen. They're asking us to draw an Aufbau diagram or an energy level diagram for nitrogen. Now, across to your periodic table, find nitrogen. I'm going to need to just clear these so that we can see, because nitrogen is down there. Nitrogen in the middle, 7. Let's go back and start working with nitrogen. It is 7 and 14. And let's just write that again. Nitrogen 7, 14. 7 meaning standing for 7 protons, and for this thing to be overall neutral, it must have 7 electrons as well. Now, if we've been asked to draw these 7 electrons, let's go to an Aufbau diagram and write them in. Across here, I've already got the blocks drawn. Sometimes that takes a bit of time, so I've already got them drawn. That would be 1s, 2s, 2p. Now, I could draw a little dotted line here to indicate to you that this is the first energy level, that is the second energy level. The second energy level has 2s and 2p. Now, I didn't speak to you earlier about what those mean. The s is standing for a spherically shaped orbital, so almost like a ball. Those electrons have a sphere in which the orbitals is shaped in. The p is a very interesting shape. It's like a figure of 8, or almost like a dumbbell-shaped figure, and it goes up and down. You'll notice there are 3 of them. Up, down, left, right, and forward and backwards. So these 3 or p orbitals together can carry 6 electrons. Let's fill in the nitrogen, and I've got these boxes. Remember, I've said to you we start from the bottom and we fill in. So 1, opposite spin, 2. That whole s orbital, that whole first energy level is now full, so we have to go to the second energy level. The next one, 1, 2, so 1, 2, 3, 4, 5, 6, 7. That is the 7 valence electrons, the 7 electrons for nitrogen. Now let's have a quick look at it and identify that as I drew these in, I didn't put the 2 of those in one of the p orbitals. I separated them out, putting 1 in each of those p orbitals because they want to be as far away from each other as possible within that same energy band. So coming back here, how many valence electrons does nitrogen have? Well, valence, remember, by valence, I'm speaking about those outer electrons, and it would be everything in this top energy level. So 1, 2, 3, 4, 5. 5 valence electrons. And nitrogen can make 3 bonds because if you look at it, it's got 3 open spaces waiting to bond. Let's turn down to another one. We've got it there. And let's look at a different one. This is for oxygen. And oxygen, I'm going to come back. We've used oxygen a few moments ago. It was oxygen 6. So let's write it up. Oxygen O had 6 and, oh, I don't think it was 6. Just check me quickly. I think it was 8. Oxygen, I was looking at carbon for a second there. We are considering oxygen, which is 8. So going back here, this should be oxygen 8 and 16. Specifically going back to the question, and I've thrown this question in to you almost as a bit of a curveball because I want you to think about it. They have asked us not for an oxygen atom, but for an oxygen ion. Now, an oxygen ion's formula would be O2 minus. The reason it's going to be 2 minus is because it's gained or taken up an extra 2 electrons, and that's vitally important. So, as we draw it, we're going to have 8 protons, but if there must be an overall 2 minus charge, how many electrons must there be? Well, overall 2 negative, so it must have 2 more, so therefore 10 electrons. Are you all happy with that? Let's come across and fill in our Aufbau diagram. So 1s, 2s, 2p, and we're going to fit these in. So in the first, 1, 2. In the second, 1, 2, 3, 4. Count so long. 1, 2, 3, 4, 5, 6, 7. Now we can start pairing up. 8. Are you happy that that would have satisfied the 8 electrons that oxygen originally had? Now, if it's taking up an extra 2, where are those extra 2 going to fit? They would be here. 9, 10. So overall, this oxygen atom has gained an extra 2 electrons, and so is overall 2 minus. You must be able to do these for ions as well as for atoms. And if I would recommend to you, as you work through these, and I've made a quick note here, if you're asked to draw Aufbau diagrams or energy level diagrams for ions, I would recommend draw the original atom, as I did. Then consider, if it's positive, it must have lost electrons because it has less electrons than protons. The proton number is outweighing, so it must have given away or lost electrons. Whereas if that ion is negative, then it must have gained or taken up extra electrons. Remember, electrons, although we're adding something, we're adding extra negatives. So it's taking up extra negatives, and so you would be able to fit those in on your Aufbau diagram. Usually when things are bonding, they are trying to make sure that that energy level is full. Okay? So if they're giving away, it's normally giving away 1 or 2 from the outer ring, so that what is left behind has a filled outer energy level. And that will take us to bonding. But let's stick to the periodic table and keep working. When we consider the periodic table, and I've got a periodic table in front of us as well, we've got this table brilliantly arranged. It's a fabulous table. I'm sure as a science student you're going to learn to love it. Maybe you'll get a t-shirt printed with the periodic table and be super cool. We want to speak about the groups of elements. And the reason we say groups of elements, and they're arranged vertically underneath each other, so in a column, okay? Those groups have got elements that will respond or react in the same way. And then going across, we have periods, okay, which are these rows. So as I turn here, I've got that for you. The vertical columns are called groups. The horizontal rows going across are called periods. I want to just mention to you the names. We have the alkali metals, the alkali earth metals, the halogens. Start to be able to link those names. Alkali earth would be alkali metals group 1. Alkali earth metals group 2. The halogens group 17, just before group 18. So do make sure that you can link in those names of the different groups. You probably learnt them a while back. The next thought I'd want to mention to you is electron configuration. Now, going back to Aufbau diagrams, do you recognize, and I'm going to take us back to this thought on oxygen. Actually, let's consider nitrogen, because we had it here earlier. Nitrogen's Aufbau diagram we had described already. But there's a shorter way of writing it. We don't want to sit and draw out little boxes forever and ever, okay, and write in these little up-down arrows. Scientists have come up with a shorter way of writing it. So the electron configuration is then given as 1s, but then how many fit in there? 1s, 2. 2s, and there are 2 of them. 2p, and there are 1, 2, 3 of them in that arrangement. So it's a shortened way of writing this. Instead of writing all the boxes out, we can just summarize it. So notice the orbital is given 1s, with how many electrons almost given as a superscript, almost like an exponent. Okay, you would write it smaller and above the line. Now I've done those for you for a few of the elements, because I want us to try and see if we can pick up some trends. Okay, so this was group 1, then group 2, the transition elements, group 13, group 14, and etc. You can go and sit and work those out. I'm not going to spend forever doing it, because I want you to look a little bit with me at some of the trends. So let's consider group 1, and I'm focusing only on this column. How do these end? S, 1. 2s, 1. 3s, 1. 4s, 1. What are you picking up? This has got only one electron in that outer s orbital, one valence electron. So, what do you notice? It happens to be called group 1. Very interesting. Let's see if this trend continues. 2s, 2. 3s, 2. 4s, 2. And called group 2. Absolutely. Let's jump across. We're going to skip the transition elements, jump across to group 13. Now, recall, we're saying everything in that whole outer band, all of the second energy level, the third energy level, not just P's and S's, will be what we would call our valence electrons. So you've got 2s 2 and 2p1, which is 2 plus 1, going to give me 3. 3s2, 3p1, going to give me an overall of 3. Now, suddenly we have group 13. What do we do? Well, actually, this 10 was for these 10 transition elements. And some periodic tables, particularly the older periodic tables, actually called that group group 3 and group 4, etc., as you went along. But now, as we've been considering this, many students have asked, what about the poor transition elements? Why don't we number them in terms of groups? So they have now in our new periodic tables incorporated those, and so we're now calling this group 13, okay, and then group 14. The same thing will apply though. So let's turn to the bottom. I've got an idea here. Points to note, the number of valence electrons, the electrons in the outer energy level, is the same as the group, okay? Numbers for group 1 to 12. That is including the transition elements. For group 13 to 17, so those are the ones in this side of the periodic table, the far right-hand side of the periodic table. You would just need to subtract 10, okay, to get to the number of the valence electrons. So you would take the group number. Let's go back to group 13. Group 13, you would subtract 10 away from that, and you're left with 3, and that's exactly the number of valence electrons there is. Group 14, you would subtract 10. Let's see. 14, absolutely. 2s2, 2p2, an overall of 4. 3s2, 3p2, an overall of 4. So for the groups on the far right-hand side of the periodic table, where they've included the transition elements, you would need to just subtract 10 to get to the valence electrons. Now let's continue. The next point I'd want us to note is that the last energy level that is filled is the same as the period. So let's just jump up here and have a look. And I'm going to clear some of these scribbles that I've made on this table so we can see it clearly. I recommend you have a periodic table in front of you as you look at these, because I want you to consider that we're going across the rows as periods. Hydrogen, number 1. Lithium, its last one is number 2. So let's go and have a quick look at the periodic table. Hydrogen is in the first row. Lithium is in the second row, or second period. Sodium is in the third row. Let's go back and see. Yes, sodium's last energy level is ending up there at number 3. The third energy level, the third corresponds to the third period. The last thing I want us to mention is P, S, D, and P blocks. We're going to finish off with this quickly, and the S block responds to those elements where they have their last valence electron in an s orbital, in an S-shaped orbital. Notice those all end in S, and these ones all end in S. And this block is called the S block. We don't do many of the d orbitals, but just so that you know, there's the transition elements. If I move across here, for group 13, notice these end always with the P's. And so the right-hand block is called the P block. As you consider these, you must think about it. The periodic table is brilliantly designed, and it's such a useful tool. If you can get all of those techniques to help you to recognize what is the electron structure, how does this relate to the periodic table. I think we need a break.
I think we're ready for a break. Atik and I have been looking at the page and we're wondering, where are all your questions, guys? During this break, please send in anything that you need to send in about the periodic table and all it entails. Guys, that's what we're here for. We're here to answer your questions. So do that during the break, don't you agree?
Yes, definitely.
Okay, see you just now, guys.
Hi there, Mindsetters. Welcome. Welcome to the show.
Don't worry, guys. Today, remember, physical science, we have something so awesome coming up. Tracy is standing right behind this awesome mindset studio thingy, and she's ready to do such a great experiment. But I want to remind you guys, ask questions right now at this point. Atik was saying, ask questions, so tell them where to find
Our
us.
fingers are getting itchy. We need
To
answer
type,
questions.
exactly
Yes.
that. So tell us where to find, tell us where they can find us.
www.facebook.com/learnextra.
Thank you, Atik. Take it away, Tracy.
Thanks, Katlego. We've got some sodium metal here. Sodium metal is one of the metals in the first group, group 1. And I want you to have a quick look here. I'm going to cut it, and it's normally kept under paraffin. This paraffin has dissolved somewhat, but as you focus on this very closely, what I want you to recognize is that there's some shininess to that. Okay? So as you have a look, and I'm turning that towards you, you should look very closely and see it is a metal. Notice that lust, that shine that we have got there on the edge of that metal. Okay? It's quite a soft metal, but we want to look at investigation today on the reactivity of the group 1 metals. And what we're going to notice, and we've got the sodium, I'm going to hold it above a beaker of water, and we're going to dip it in the water. I want you to recognize how reactive this metal is. Okay? Are you ready? I'm going to drop it
ready.
in.
I want to see what happens to
I
this.
think I might need to step back from this. Are you ready?
Ready?
Let's go.
Wow.
Wow. Do you recognize it fizzing along the top surface as it's reacting, producing hydrogen gas, and that hydrogen gas is making it fizz and bubble.
Wow.
It is incredibly reactive.
So is that very dangerous if you touch it or if you do anything?
Well, absolutely. You might have noticed I wasn't touching that with my fingers
Yes.
because I've got moisture on the edges of my fingers. We've all got a little bit of moisture on our fingers, and so it would react with the moisture on the water on your fingers, and so it would possibly burn you. It creates quite a strong base, which is, in this case, it will be sodium hydroxide. And so if I put a little bit of universal indicator in this water, it would also turn that deep purple color. Do you want me to do another little one?
I think we must.
I think we
was
should
fun.
too. That was good fun. Let's see. I know my class at home would be saying to me, "Oh, ma'am, oopsie, put lots in."
Yeah, I'm thinking just put everything in there so that we can see it bubble up.
Well, we don't really be wanting to put everything in because we don't want to create a huge explosion, and
okay.
I am not wearing safety glasses, so I don't want to be
I see.
having
Next
any of
time-
that
next
come in
time we'll
my
get you
eyes.
safety glasses and the full gear and everything.
Be cool. But recognize there a very, very strong reaction with water. If I had some of the other elements in the periodic table in group 1, let's turn back to the board. We were working with sodium, and we found it had a strong, I'm not going to call it a violent reaction, but quite a significant reaction. Significantly reactive, pretty significantly reactive. Potassium would be even more reactive. The next one down, rubidium, cesium, francium, we're not even able to get our hands on, because as you go further down that group, they all respond in the same way, but to a greater extent. So if I worked with lithium, much less. If I worked with sodium, it's a strong reaction. Potassium, significant reaction. And so it continues. Let's start to now talk about trends in the periodic table. By trends, I'm meaning patterns, things that are found in the periodic table. So we've got some key words here. This is terminology you need to know and understand. By atomic radius, I'm meaning the size of an atom. From the center to the outside would be the atomic radius. If we spoke about the diameter, from one edge to the other edge. The next idea relates to ionization energy. Now, what does it mean to form an ion? An ion would be something that has got a charge, positive or a negative charge. So ionization energy would be the energy that is needed to remove one electron from an atom in the gas phase. And you could also do the first, so that would be first ionization energy, or we could do second ionization to take 2 electrons out, or the third ionization to take a third electron out. The ionization energy is specifically the energy needed to take an electron away. The last one I want us to speak about is electronegativity. And by electronegativity, we're speaking about the tendency of an atom to pull or to attract an electron. And usually we are meaning this in a covalent bond between 2 atoms, how badly it wants to pull that electron closer to itself, or that pair of electrons closer to itself. Let's have a look at these trends across periods. So along the periods, these would be our rows. So from the left-hand side across to the right-hand side, we see the pattern is that electronegativity increases. And I want you to think about this. I'm picking fluorine, which is up here on the periodic table. It has got, I'm going to just choose a different color. Fluorine is up here on the periodic table. It has got F9. So if you have a quick look at its electron structure, and I'm going to just draw the concentric circle model because I know it's quite quick. So we've got 2, 1, 2 in the first, 1, 2, 3, 4, 5, 6, 7, 8. Hold on, I think that was too many. Let's just have a quick look. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a total of 9. Okay? What I want you to consider is that fluorine is very close to having a filled outer energy level. It's so close to having a completely stable electron structure, which is a filled outer energy level. So if it just got one more, and I'm going to draw it in there as a cross, if it just got one more electron, it's sorted. Now, because it's so far along here, and actually it's a little bit closer to the edge, pretty much there, its electronegativity is very high because it really wants to take an extra electron up. It really wants to grab an extra electron, and so it's going to have a great tendency to pull that electron close to itself. Ionization energy, remember we said it's the energy needed to remove an electron. Fluorine is so close to getting a filled out energy level, it doesn't want to give away any extra energy levels, so you would have to require very large amounts of energy, high amounts of energy, in order to take an electron away from it. Whereas these guys over here, let's pick lithium, has only got an one valence electron anyway. So it doesn't mind giving that away, and it wouldn't require a huge amount of energy in order to do that. Atomic radius. Well, again, and I think I should draw lithium. Let's just draw it over here. Lithium is 3, so Li, 2 rings, 1, 2, and I'm going to draw this last one over there, 3. Its atomic radius is quite small, and you'll notice the trend in the periodic table is that it increases as we go to the left, whereas decreasing that side. And the reason for that is how much it's pulled towards the positive center. So from the nucleus, how much that those outer valence electrons are pulled to the center. Let's look at some trends going down a column, i.e. within a group. So we started by doing this little experiment to look at sodium with water, and we said it was a strong reaction. Let's come across and look at why that could be. So I'm now looking in group 1, because that's where we had sodium. Sodium was, we said, quite reactive. But as you go to the next one, potassium, even more reactive. The next one, even more reactive. And so we can't even get our hands on them because they would create such violent reactions as they react with water. They all undergo a very similar reaction, releasing the same products, but in terms of how reactive they are increasingly reactive as you go down the group on this left-hand side. So atomic radius, what do we mean by that? Well, we mean how big this atom is from the center to the edge, or if we're talking diameter, from the edge to the edge. The atomic radius increases as you go down the group, so it's high at the bottom and it's low at the top. Why would that be? Well, again, go back to the concentric circle model. Go back to drawing out these maybe energy level diagrams. And as you can do that, you can recognize that as you go down the group, you're adding an extra energy level every time. And so this atom is getting larger and larger. And so what you will notice is that the radius is getting bigger and bigger. The next one, ionization energy. Ionization energy is the energy needed to take an electron away. Now, if I go back and draw, and let's draw lithium quickly, Li, and I'm going to just quickly show you, that has only got 2 energy levels, whereas for something like sodium, it's got 3 energy levels. It's going to be holding this 1, 2, I think it's got 11. Let's do these quickly. Okay, that outer that outer electron, that valence electron, is held far away from the nucleus, a far distance away, whereas this one is held closely. So this valence electron is very close and is pulled towards the nucleus with a strong attraction, whereas this valence electron is much further away and so is not held with as much of a force of attraction. And so to remove that valence electron would require much less energy. Electronegativity. Electronegativity increases as you go higher up the group, or is highest at the top. Again, the same reason, because if you consider the nucleus in the center is closer to that valence electron, and so it will hold it and attract it furthermore, and attract an extra electron, if necessary, even higher up. I think that's pretty close to what we've got time for. Remember, as we go through these trends, that you need to often, and I highly recommend drawing the concentric circle models as you try and think about and explain why we have these trends.
Tracy, a question.
Yes.
People have been asking, I know Isaac has just asked, how many elements are we required to know, and what's the quickest way of grasping them all and learning them all?
You will always be given a periodic table, unless you may be being asked to remember the symbols or something like that, just in terms of naming them. But in a test or an exam, almost always you'll be given a periodic table. So I would recommend that you know the names at least, and you get familiar with the first 20 elements. That is up to calcium, so hydrogen through to calcium. That's a very good start. There are some others that we work with often: copper, silver, gold, those ones which are we probably would become familiar with.
Yeah.
But I would recommend, in terms of identifying them, knowing them well, the first 20 should stand you in good stead.
Oh, okay. And then, who's this? Votivu asks, what's the difference between representing a molecule and an ion in an Aufbau diagram?
Okay. A molecule, probably not the very good word. We normally would be speaking about an atom or an ion. An atom would be electrically neutral, whereas an ion would have either a positive or negative charge. So by an ion, you are probably thinking there you would need to gain extra electrons, and we went through one of those. So I'd suggest go back and check that out. We went through an oxygen ion, whereas an atom would be electrically neutral, so no overall charge. But for all of them, I would recommend start with the atom as electrically neutral, and then at the end, go back and see if you need to add in or subtract away.
Okay.
But that's
Thank
all we've
you,
got time
Tracy.
for, mindsetters.
Thank you, Tracy. Thank you, guys, for joining us. Thank you, Atik, for doing that.
Thank you
Are you
very
okay, or how was it?
It was great. I had a very good time. And it was quite informative. I learned a lot of new
And
things.
yeah, I know your physical science, you probably loved it. Guys, thank you for joining us. Call all your grade 11 people to join us for the next show. Remember, same time, same place next week. Bye-bye.
Circle model. For the concentric circle model, we are considering energy levels with the electrons found on those energy levels or in those energy levels as circles, concentric circles. And in the first ring, 2 electrons can be found. In the second ring, 8 electrons can be found. And in the next ring, third ring, 8 electrons can be found. And we're not going to go much further than that. So let's have a look at how this would be done. I've got an example here of neon. Neon has 10 and a number 20. What do those numbers mean? We spoke about this last week. The 10 represents the atomic number. Okay? Which means the number of protons. Positive. Okay? The 20 represents the atomic mass. And I'm going to change color to indicate that it would be atomic mass. And for atomic mass, you are thinking that is the protons and the neutrons. As we have a look at that, if it's got 10 protons, for this atom to be neutral, if it's got 10 protons, how many electrons must it have? Well, for it to be perfectly neutral, it should have 10 electrons as well, so that overall the charge is 0. There is no charge. So let's go with this atomic model and fill in the electrons. We're going to fill them in as little circles. I said 2 in the
Hello guys, welcome to Learn Extra Live Grade 10 Physical Science. Finally, your day has come for your favorite lesson. I'm Katlaho and this is Atik. Hello Atik.
Hi, Kileko. How are you doing?
I'm great, thank you. Guys, Atik is one of our top 10 presenters. He will be joining us for the entire show today. He's really excited, aren't you?
I'm ecstatically excited.
Exactly, so you guys need to get chatting. Please tell them where they can find us.
www.facebook.com/learnextra.
Awesome. So you guys know the drill. Jump onto the page, get chatting to us, ask questions, ask anything that you need, because that is what we're here for. Today you have both of us, so make sure that you have as much fun as we have. Of course, you're seeing right. We have our Simba, can you see those? Yes, Simba Cheetos. It's really awesome. I've been dying all week, like even last week, just to have like one packet of these. But these are for the random acts of kindness, guys. You guys are, you just urged or asked nicely to post some pictures on our Facebook events wall of anything that you have, any random act of kindness that you can do for anyone in your community and beyond, guys. It doesn't take much of your time. It's just a smile. Or what can you think of, Atik?
Maybe helping a little brother or sister do homework.
Exactly. Plus you're a mindsetter, so you know more than they do. So jump on to the page, send us your random acts of kindness, and you can stand a chance to win this entire hamper. Now this hamper has chips, it has a mindset lanyard, it has a mindset pen, it has a Cheetos notebook.
the arrangement of the periodic table with atomic structure, link periodicity, which means the repeating patterns of the table to the various chemical properties of the elements, and learn about trends. So, let's get stuck into electron arrangement. Electrons are found in energy levels. And when we say energy levels, we're thinking those ones that are closest to the nucleus will have the least amount of energy. And as the electrons are found in energy levels further away from that central nucleus, they will have to have higher energy. They would be moving in regions of space that are called orbitals. Now let's just take this little bit away so that you can note this very important word, orbitals. Orbitals are regions of space where an electron could be found. There's a higher probability of an electron being found there. They are not spherical rings or different shapes, but they are clouds, electron clouds where electrons could be found. There are various ways that we can represent electron configurations, and we're going to discuss 3 of those today. We're going to look at a concentric circle model, a Lewis diagram, and an Aufbau diagram, and this is also called an energy level diagram. You could very easily in an exam question be asked to draw these models. And so not only are they important for your understanding of bonding and everything else that's going to come in chemistry, they are important in terms of answering exam questions. You will be asked to draw these. So let's start with the simplest, the concentric.
It has 5 cities, guys, not just 5. It has Unati, it has Malik, it has Kaya, it has Donald, and it has some love song because it is the month of love and we are spreading love. So make sure that you are the one that wins this package, guys, because it's really, really awesome. Today we're doing physical science with Tracy. Tracy, how are you?
I'm doing well, thanks, Katlego.
Awesome. Please tell us what we'll be doing today.
Brilliant. Well, mindset is it's really important that you pay full attention today. We're going to be looking at electron configurations and the periodic table. And electron configurations are something that is fundamental in terms of your understanding. Grade 11s and grade 12s often still struggle with this. So I really highly recommend that you take out that exam pad, that you've got your pen and notepad ready, that you've maybe downloaded the notes already, and that you're going to be working really, really well with me today. Katlego, anything else?
And nothing else. You can actually just take it away. I'm sure they're dying to know what's happening today.
Absolutely. Well, thank you so much. We are really, really looking forward to this. And as I said to you, chemistry, in terms of all the bonding that you can ever do, chemical reactions, it's so vital that you make sure that you have a very, very good understanding of electron configuration. So let's get into it. Electron configuration and the periodic table. This is a simple periodic table that we've got in front of us. What we're going to be learning today, we'll be focusing on drawing electron configurations. So by electron configurations, I'm looking at how electrons are structured around atoms and various models or pictures that help us to understand those. Show that elements are arranged in increasing atomic number on the periodic table. Link first, so 1, 2, in the first. Now we go. 8 in the next, so 1, 2, 3, 4, 5, 6, 7, 8. Check with me quickly. Is that a total of 10? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A total of 10 electrons shown in those energy levels. Now, the reason I've shown this one to you specifically is because I want to indicate to you how to arrange them. The electrons I want to recommend is that you put those electrons on the compass points as you work your way around. It's going to be very helpful to you because it's going to show how many spaces there are available for bonding. And we often use something called the octet rule, which is saying if you've got filled outer energy level full of, in this case it would be 8, and apart from helium, which has only got 2, so it's only the 2 in the central ring would be filled. If it's got this filled outer energy level of 8, almost like 8 people sitting around a table, there is no more space for any electrons. So there's no need for that atom to bond. And neon actually is one of those noble gases. It doesn't bond with anything else because it's got a stable electron structure, a filled outer energy level. So we've got two key words that I want you to note: valence electrons and core electrons. What do you think the core electrons would be meaning? The core electrons must mean the inside ones, right? So the core electrons in this case would be neon's 2 core electrons. They would be